Hello everybody, I hope you're all doing well. So we're going to be solving a problem on rigid body kinematics, and this is going to use the idea of rolling without slip. Okay, and here I have several things that are drawn together. I wanted to have this problem drawn before we start tackling it. Okay, so I just want to point out a few things. So at A there is a slider. Okay, so this is a slider between guides. Okay, and then this is the disk, and lastly I have this block here, which I labeled as B. Okay, so this is a block. All right, what's going on in this problem is that this slider is performing vertical motion between these fixed guides here. Okay, and we are given some information regarding the motion of the slider. We are given some information regarding the motion of the block, and then we need to compute what the angular velocities are of certain quantities. So let me write down the problem as such. Okay, so the slider moves downwards with a constant speed of 6 meters per second. Okay, so given the slider A moves down at a constant rate of 6 meters per second. Okay, that's the first thing that we are given here, and understand this, that the slider is performing rectilinear motion and it's traveling at a constant speed, which means you obviously know its acceleration, right? And its acceleration is going to be 0, and the slider is connected to a circular disc. Okay, so the slider is connected to a circular disc of radius r is equal to 1 meter. Okay, as you can see, by means of a bar OA. Okay, and this bar is a rigid bar. Okay, so let's write that down. So rigid bar of length 4 meters. Okay, and at that instant in time, the bar OA is in the position drawn okay, as I'll go to the figure, you'll see that at that instant in time this bar OA is in a position drawn. So what this means to us is that at that instant in time, this bar OA is making an angle of 45 degrees with the horizontal. This is at that instant in time only. So this is almost thinking of a time shot of the entire spectrum of action that is taking place here. Okay, and so all these values that you're given are at that instant in time. Okay, and then one more thing is that the block B is moving to the right at a rate of 3 meters per second and is slowing down at a rate of 4 meters per second square. Okay, so you're given the velocity of the block. As you can see, the velocity of the block is given to us as 3 meters per second square. Let me not write this as a vector because I haven't defined my coordinate frames yet. So this is 3 meters per second, and then here is the acceleration, and I'm told that the block is slowing down, which means that if the velocity is pointing to the right, the acceleration will be pointing opposite to that. This is mostly because the block is performing rectilinear motion as well. Okay, and so this is going to be at a rate of 4 meters per second square. Okay, so that's decelerating at this particular rate. And the last piece of information here, the disk rolls without slip on the block. Okay, and what we need to find on this particular problem. So disk rolls without slip on the block, and I just want to point out that the point C is a point on the disk, B is the block which is right underneath the contact point. Okay, so contact point between the disk and the block on the disk is labeled as point C. On the block I have labeled it as point B. I mean, I can just call it as anything on the block because all the points on the block have the same velocity and acceleration. Okay, so the key statement here is that the disk rolls without slip on the block. Okay, that's something that is going to help us solve the rest of the problem. And what am I supposed to find out in this particular problem? So find, and always notice whenever you're finding something, you're finding it at that instant in time. Okay, so at that instant in time, okay, find the angular velocity and angular acceleration of the rod and the disk and the disk. Okay, and in doing so we will find other things as well that will be of use to us. Okay, so I'm going to copy my figure once again and then we'll very briefly go over it. I'll try to not copy some of the other extraneous information that I don't necessarily need. We know what is a block, we know what is a disk, and all those kinds of things, right? Okay, I'm going to bring this down, and let's say we're going to start the solution. Okay, whenever we start the solution, we need some kind of a strategy. Sometimes we don't have a strategy, so we just say, okay, I'm just going to make use of all the equations that I typically know, and then hope to God that it works out. Okay. All right, so I'm going to bring the figure once again here, and I'm going to set it up somewhere in the corner. The first thing I typically do is I typically draw my triad, okay, my triad of unit vectors with respect to a fixed observer. Okay, so I'm going to draw a fixed observer somewhere here, and here is my triad. Okay, so I'm going to call this as I, I'm going to call this as J. That J did not work out too well. Once again, okay, J and then K, and then I also know that I cross J is going to give me K and so on and so forth. So I just write out and say, okay, hey, here is the triad I, J, and then K. Okay, and as you recall, a triad is a set of unit vectors that are mutually perpendicular to each other. Okay, such that if I do I cross J, if I do the cross product, okay, then I get K. And I have to follow the direction of the arrows that I have marked here to get the positive value. If I go against the arrows, I get the negative value. Okay. One more thing I also do is at the contact point, okay, between the block and the disk, at that instant in time, I'm going to set up a coordinate frame. Okay, so let's see. So at that point in time, let's do it in this red color here. Okay, so at that point in time, I'm going to have a direction this way, and then I'm going to have a direction this way, right? So this is going to be my tangential direction, and this is going to be my normal direction. Okay, and something that I will also say is at that instant in time, the t and n directions at the point of contact, these are coincident with the I and the j directions. Coincident with the I and j of the inertial frame. Okay, so this is only at that instant in time. Please notice this. At the next instant in time, that frame would have rotated because it is a part of a frame attached to the disk. Okay, so at that instant in time, I can say the following. At the instant shown, I can say that t direction is the same as I, the n direction is the same as j. Okay, this is once again only at that instant shown. Please notice that. Okay, so this I have done, and then I can also write out the conditions of rolling without slip. So that's an information that is given to me in the problem. Okay, so I'm told that at that junction there is rolling without slip. Okay, so that's the first thing that I look at. And so if I make use of the idea of the rolling without slip, okay, so rolling without slip, and then I'm going to just recall information from before. Okay, so point C is the contact point on the disk, point B is the contact point on the block. As you can see here, point C and point B, right? This is the point that I'm talking about. Okay, this is the contact point there. And if I have the idea of rolling without slip, then the criteria to be satisfied is this: velocity of C/B has to be 0. Okay, this is the fundamental criterion for rolling without slip. And velocity of C/B is equal to 0, which tells me that velocity of C should be equal to velocity of B. Okay, that's the first thing. Now I can also do the other one, that is the acceleration of C/B in the tangential direction is equal to 0. Right, that is the second criterion for rolling without slip. Okay, the relative velocity at the contact point is completely 0. Okay, this is the first criterion. The second criterion is that the relative acceleration in the tangential direction is equal to 0. The normal acceleration is not necessarily 0 because the disk has to peel off of the surface of the block. Otherwise, then the system will be in static equilibrium. If the entire velocity is 0 and if all the acceleration is 0, then you're solving a problem in statics, and hopefully that brings out good memories in you. Okay, but that's not the case here. But we just have this condition satisfied. So this tells me that acceleration of C in the tangential direction is equal to acceleration of B in the tangential direction. But I know T is the same as I direction at that instant. And so look at this. Acceleration of C I can write as acceleration of C in the I direction, acceleration of C in the J direction. Okay, this is the same as at that instant in time. Okay, this is the same as acceleration of C in the tangential direction, acceleration of C in the normal direction. Acceleration of C in the tangential direction is the same as acceleration of B. Okay, so here is what I have. Acceleration of C is now acceleration of B in the I direction and in the J direction. I'm just making use of the fact that these two quantities are the same. Okay, so I'm just substituting for that. Okay, and then I'm saying, okay, instead of T and N, I can also write this as T and N if I want. I don't need to. I can work with the coordinates of the inertial frame, or the unit vectors of the inertial frame. So I wanted to write it as T and N. So if you want, you can also write it this way. Okay, Cy in the n hat direction. Okay, so we will work with we shall work with the IJK system. Okay, so these are the two things that I know now. Okay, so velocity of C is the same as the velocity of the block, and then this is the acceleration of C. Okay, and I have written it in terms of the acceleration of the block, and I know that the block is accelerating only in the horizontal direction. So now I'm going to make use of the information given to me. Okay, so from information that is given, okay, once again I'm going to put a line here and underline it, and you'll see that the problem becomes very simple once we start doing it. From the information that is given, I'm going to go here and then look at the first piece of information. Slider A moves down at a constant rate of 6 meters per second, which means that its velocity is pointing in the vertical direction at that instant in time, and which is the minus j direction, right? So slider A has a velocity which is pointing down. So I can maybe mark that here as well. Okay. So velocity of A is 6 meters per second. So I'm going to write that down here. So I know that velocity of A is 0I minus 6j, so many meters per second. And since slider is moving at a constant rate, you're told this in the problem statement. You can go and take a look at the beginning of the problem. Slider A is at a constant rate, which means that the acceleration of A is 0I and 0j meters per second square. Okay, this is because the slider moves at a constant rate. Okay, then the other piece of information that I was given was the velocity of the block was pointing to the right, and this was taken to be 3 meters per second. So this is 3I and then 0j meters per second. And then the acceleration of the block, we were told the block was slowing down at a rate of 4 meters per second square. If the block is traveling to the right and slowing down, then its acceleration is going to be in the negative direction, meters per second square. Okay, this was also information that was given to us. And then results from rolling without slip due to roll without slip. Here is what we have. Velocity of C was equal to velocity of B, right? As you would have seen from here, velocity of C is equal to velocity of B, which tells me that velocity of C is going to be 3I and then 0j meters per second. Acceleration of C was acceleration of B and acceleration of C in the y direction, some component in the y direction. Acceleration of B was minus 4I, right, in the I direction. So this is in the tangential direction. This was the situation. So this is now going to be the following, which tells me that acceleration of C is minus 4I ACY J. Okay, but if you want, you can write this as acceleration of B in the tangential direction, and this is the acceleration of B. Let me mark it in a different color. This is the acceleration of B in the tangential direction. Maybe you can do the same thing here too. You can say that, okay, this guy is acceleration of B in the tangential direction. Okay, if you want. That's the proper way to do it. Okay, if you want to be really strict and rigorous about it. All right, so here is all the information that I have. Okay, this is all useful information. Now I'm going to assume a couple of things. Okay, I'm going to go to the problem here, and then I'm going to assume that the disk is rotating at a certain in a certain direction. Okay, so I'm going to assume that here is what I'm going to assume. Okay, I'm going to assume that this is the omega of the disk and this is alpha of the disk. Okay, I'm going to assume both of them to be clockwise. So this is assume. Okay, so assume the directions because I don't know. This is something I'm supposed to find out. And likewise, I'm going to assume the same thing for the bar here. I'm going to assume that this bar is rotating counterclockwise. I don't know. I could be wrong. Okay, so I'm going to assume this to be omega of OA. and I'm going to sneak this information in here. Let's see if I can move that somewhere here, or I'll just cut that off, because I'm just trying to have one more direction drawn, and I'm going to assume that this is the direction of alpha. Okay, so maybe I can take this guy and then put it down here. Okay, and here is alpha OA. Okay, that's the angular velocity of the bar. I'm just assuming the angular velocity to be that way. Okay, so let me then write this down as well. Okay, so based on the assumption, look at this. The direction that is coming out of the page based on the inertial observer here is the k direction. If I assume something counterclockwise, then that is going to be in the positive k. If I assume something that is clockwise, that's going to be in the negative k direction. Okay, so this is an assumption that I'm making with respect to the angular velocities. Okay, so I'm going to assume, and that is completely fine. As to what direction I think it's going to be, I don't know, because I don't have any premonition of what's going to happen in life, right? If you do, please contact me. All right, so I'm going to assume that omega of the disk is going to be minus omega disk in the k direction. Alpha of the disk is going to be minus alpha disk in the k direction, and I'm going to assume that omega of the bar is plus omega in the k, and then I'm going to assume that alpha is alpha in the k direction. Okay, so these are all assumptions that I'm making. Okay, so I'm assuming it to be clockwise, and this is assumed counterclockwise. Okay, so we have a lot of information that we have collected. Okay, and I'm going to bring my figure once again down. Hopefully that makes some sense. Now that we have a lot more done on this particular figure, so I'm going to copy that and I'm going to bring that down here. Okay, so every time I look at what to do in this problem, I have to bring my figure down and see, okay, what is my strategy? So what could be a strategy? Here is what I typically think. Can I find a common point on two rigid bodies here? Of course I can, right? This point O is a point on the disk. The point O is also a point on the bar OA. Okay, so that's something to be looking out for. So a strategy, this is a strategy for pretty much many of the rigid body kinematics problems, is try to find a point that is common to two bodies. Right here, of course, there is also the choice that the point C and the point B, but we have already taken care of it, right? So a good choice would be point O. Okay, so point O is a point on the disk, and point O is also a point on bar OA, right? And then the strategy is fairly straightforward. I write the velocity of point O using information from the disk. I write the velocity of point O writing information from the bar OA, but this is the same point, which means that those two velocities have to be the same. Okay, so this is the strategy that I'm going to employ. Okay, and then here is what I'm going to do next. Okay, so let's write the velocity of point O. So for that, I need to have the figure shown here. So let's say, so first one, so point O on the disk. So look at the disk first. And if you want, you can just capture only the disk and then bring it down here. That is completely fine as well. Let's see if I can do that. Okay. I don't know if this will work out, but let me just leave it like that. Let me leave it alone. So look at the disk. Point O and C are on the same body. Okay, so O and C on the same disk, which means that the velocity of O relative to C is 0, and you obviously know that the acceleration of O relative to C is 0. That is, the distance between these 2 points is not changing, right? And that's what this typically says. Okay, so maybe I should write that down as well. So this implies that the distance between O and C is fixed. Okay, so that's the meaning of that. And then I try to relate the velocity of these 2 points. I make use of the generic formula. Okay, velocity of O is velocity of C, velocity of O slash C relative due to the change in the distance between the 2 points, which is 0 here. And then I'm going to have omega of the disk crossed with the position vector, okay, from point C to point O. I'm looking at point C as the observer and drawing a position vector to the point O. And obviously I know that this creature is going to be gone. Okay, and so I can continue forth and then say velocity of O is velocity of C plus omega of the disk crossed with R O slash C. Okay, and then if you want, you can also do the following. Let me quickly draw the disk here. Okay, so here is the disk. Okay, it doesn't matter what the color is. The disk is a disk, right? Point O, and then here is point C. The position vector is going to be drawn from point O to point C. Okay, so this is going to be R O slash C. Okay, and then if you look at the unit vector system that you have, you're going to have the I direction pointing this way, you're going to have the J direction and the K direction, right? So this is I, J, and then this is K, which means that I can rewrite this in the following manner. And velocity of C I already know, right? So we know velocity of C, if I go back up a little bit, I had a host of information written down here. So velocity of C was 3I plus 0J, right? So that's going to be 3I. So many meters per second. Okay, and then I know that I have assumed omega d to be minus omega dk, and then R O slash C. Look at this, I'm sitting at the point O going to the point C, sitting at the point C going to the point O in the positive J direction. So this is going to be R times positive J, and the radius of the disk is 1 meter here. Okay, that is 1 meter, so this is going to be 1 times J, so many meters. Okay, so this is what we have. I'm going to substitute this back in there, and so I get V naught is equal to VC, which is 3I plus 0J plus minus omega of the disk K crossed with 1J. Omega of the disk is not known to me. Okay, so this tells me that velocity of O, and I can look at my triad. I'll bring my triad. Okay, if I look at my triad, I don't go anywhere without my triads. Okay, so if I look at this, this is going to be 3I. K cross J is what you need to look at. Okay, so look at K crossed with J. What is K crossed J is minus I, but I already have a negative sign, right? So this is going to be 3I plus 0J minus omega d times 1 times K cross J, which is minus I. So minus times minus is a plus. Okay, let me write this multiplication here. Times 1, K minus times minus is a plus, so this becomes an I thing, so which tells me that the velocity of point O is 3 plus omega of the disk in the I direction and then 0 in the J direction. This is quite obvious. The disk is not going to have a velocity in the J direction. Okay, so this is so many meters per second. So this is one thing that I can take from here. Then I can do another thing as well. The point O is a point on the bar too, right? So I'm going to look at that. Look at the bar OA. Look at the bar OA. Okay, O and A are on the same body, which implies that velocity of O slash A relative is equal to 0. Acceleration of O slash A relative is also equal to 0. Okay, and if I make use of the relationship between velocities of O and point A, so then velocity of O is velocity of A, velocity of O slash C relative, and then omega of the body that I'm interested in, which is now this bar OA, corresponds with the position vector from A to O. Okay, and once again this creature is gone. Okay, and let me maybe just grab the bar OA and the disk and the body here. Let me maybe bring these two guys down. Just these two. Okay, so I'm going to copy that and bring them down here. Okay, so that we can start analyzing them a little more. Okay, so here is what I have. I don't even need the disk if you really think of it, because I'm not interested in that. I'm going to cut that off. I'm going to cut that off as well. I'm going to take this and put it down there. Okay, all right, and this is what I used to write the velocity expressions and so on. Okay, now omega OA is given to me as I'm assuming it to be positive, so let me see. VA is known to me, so VA is minus 6j so many meters per second. Omega of OA, I'm assuming it to be omega OA in the k direction. Okay, then alpha, then the position vector from O to A. Right, so here I want to be a little more explicit or careful. Okay, so I'm just going to redraw it. Okay, so this is 4 meters, and this is the point A, and this is the point O. Okay, so RO slash A, I'm sitting at the point A and then I'm looking at the point O, which means I have to go down and then I have to go to the right. Okay, so if I draw the arrows, then this is going to go this way, this is going to go this way, and then eventually this is my position vector. So this is going to be RO slash A. Okay, this angle was given to me as 45 degrees at that instant in time. So this is going to be something in the positive direction. So this is 4 times cosine 45i minus 4 times sine 45j. So many meters. I'm sorry, I shouldn't be doing that. So this is 4 times sine 45j. This is so many meters. Okay, so I'm going to take this and substitute this back into the expression for V naught. So V naught is going to be minus 6j, and then I'm going to have omega OA in the k crossed with 4 times cosine 45 and sine 45. Okay, these are 1 by root 2. Okay, so I'm going to make use of the fact that cosine 45 is equal to sine 45 is equal to 1 by root 2. Okay, so this is going to be 4 by root 2i minus 4 by root 2j. I'm going to do the cross product. Take my triad with me, as I said, everywhere I go. So I'm going to copy that. Excuse me. It's the early morning jitters. All right. So I got V naught is minus 6j, and then look at this. Omega OA times 4 by root 2. And I'm going to do k cross I plus omega OA times minus 4 by root 2, and I'm going to do k cross j. Okay, this is what I have, and I look at the triad and I say, okay, hey, k cross I is j, and then k cross j is minus I. So if I do the substitutions, I get V naught is minus 6j, k cross I is j, so this is 4 omega OA by root 2j, and then I'm going to have k cross j is minus I, but I already have a negative sign, so this is going to be 4 by root 2 omega OAI, or if I write everything nicely, V naught is minus, let me write it from the I direction, 4 by root 2 omega OA in the I direction, and then this is going to be 4 omega OA by root 2 minus 6 in the j direction. Okay, and so this is the other one, and just so many meters per second. Okay, I'm not sure why they disappeared, but It's back and we are back. Okay, so now I'm going to take my expressions from the previous velocity analysis as well. So here is what I have. Okay, so I have two expressions. I'm going to copy that. Okay, so far what we have that this is known to me. This is from one body, this is from the other body. Okay, so I'm going to copy that and I'm going to paste that here. So we got this from the disk, this is from the bar OA, but obviously these two velocities are the same, right? Which means that I'm just going to equate them together. Okay, so this tells me that 3 plus omega disk in the I direction, okay, plus 0j, this is equal to 4 by root 2 omega A in the I direction plus 4 omega A by root 2 minus 6 in the j direction. And then I say, okay, equate the I terms, equate the j terms. Okay, I'm going to start with the j terms because it looks easier to me. So 0, I always like terms that have zeros in them, omega OA by root 2 minus 6, which means that I can solve for omega OA. Okay, 6 by 4 times root 2. Okay, so this gives me omega OA as 2.12 radians per second. I obtained a positive value which tells me that the direction I guessed was correct. Okay, then I go to the I direction, I get 3 plus omega of the disk is equal to 4 by root 2 omega OA. Okay, which implies that omega of the disk is 4 by root 2 omega OA minus 3. Or if I do the substitutions, substitute for omega OA in there, and I get omega of the disk to be 3 radians per second. Once again, I get a positive value, okay, which tells me that the direction I chose was correct. Okay, so I want to make a note of that. We obtained a positive value for omega OA and omega D, which tells us the direction we chose for omega of the disk and omega OA was correct. Okay, which tells me that if I now write them as vectors, omega OA is omega OA k, which implies that omega OA was 2.12 k radians per second. Okay, so this was one of the first answers. Then the second one is omega of the disk, we assumed it to be this way, which tells me that omega of the disk is minus 3k radians per second. Hope this makes sense to everybody. Okay, so I'm done with the angular velocity analysis. I will do exactly the same thing for acceleration analysis. My strategy is no different from what I have done so far. Okay, so acceleration analysis, to find next is we shall use the same idea to find the acceleration of alpha, acceleration alpha OA and alpha disk. Okay, so that's what I'm going to be doing. Alright, this time let me start with the bar OA because of I don't have anything better to do, right? So I'm just going to grab some information from earlier on. Okay, so I'm going to take some of these things. I want to take my figure as well here. Okay, so I'm just copying the same thing and just bringing it down here. Okay, so this is what I'm starting off with. That's my first thing. Okay, now I'm done with omega OA, so I know the direction, and I'm going to write the general acceleration expression. So acceleration of O is acceleration of A, and then I'm going to have what else? I'm going to have alpha OA crossed with R O slash A minus omega square OA, the scalar quantity, multiplied by O slash A. I'm going to have A O slash A relative, and then 2 times omega cross the relative velocity, but we know that this term is gone, that term is also gone. Okay, we further know that the acceleration of A is 0, right, because the slider is traveling at a constant rate. Okay, and this was a constant rate. Slider is performing rectilinear motion, which means that I can also take off this creature here. So I'm left with two very nice things. And I also know from before, you can scoot back up and then see, I also know that our O slash A is going to be 4 by root 2I and 4 by root 2J, so many meters. If you want, you can bring this figure from here. Okay, so I can bring both these creatures from there. I'm going to copy that and let me bring that down here. Okay, so this is also known to us, and so I'm just going to start substituting. So acceleration of O is going to be alpha OA cross R O slash A. Okay, now let's see what I can do here. So alpha OA is alpha OA in the K direction crossed with 4 by root 2I, 4 by root 2J, and then I'm going to have minus omega square OA, which is 2.12 square. Okay, we found out, right, omega OA was 2.12 radians per second, and this is multiplied by 4 by root 2I, 4 by root 2J. Okay, now so I can rewrite this the K cross I, K cross J. Let me do that very quickly. So acceleration of O is going to be the following. I'm going to do this cross product quickly. Look at this. K cross I, I'm looking at the first K, this is the first I, K cross I is J. So I'm going to look at the I direction. So K cross J is minus I, minus and minus becomes a plus. So this is going to be 4 by root 2 alpha OA, and then I'm going to have minus 2.12 square times 4 by root 2 in the I direction. Okay, all of this in the I direction, and I'm going to have something in the J direction as well, plus K cross I is J, so this is 4 by root 2 alpha OA, and then minus and minus becomes a plus, so plus 2.12 square times 4 by root 2 in the J direction. Okay, so this is what I have. Now so I can put a line underneath this, and then okay, so this is the situation that we have here so far. What I also want to do is the following. Okay, I know that the point O is a point on the disk. Okay, so we know O is a point on the disk. So what does that mean? And I know that the point O, if I go back to the disk here, let me quickly go back to the actual figure here. Okay, I know that the point O is a point on the disk, right? And I know that if the disk has to roll without slip on the surface, without losing contact with that surface, then the acceleration of O cannot have a component in the J direction. Okay, the acceleration of the point O cannot have a component in the J direction, otherwise the disk will lift off of the surface and the problem will be gone. Okay, so I'm going to write that statement down here. So as to ensure that the disk is rolling and not lifting off of the surface of the block, acceleration of O cannot have any value in the Y direction. In the J direction, which implies that acceleration of O is something in the I and nothing in the J direction. Okay, so this has to be a criterion that has to be met depending on how the disk is rolling, right? And which means that I can do the following. I can take this and then substitute it up here very quickly. Okay, so this tells me that a naught in the I direction plus 0 in the j direction, this is equal to 4 bar root 2 alpha OA minus 2.12 square times 4 bar root 2 I, and then I'm going to have the rest of it here. Okay, I'm just going to copy it, getting a little lazy here. Bring that down. Okay, that's stuff in the j direction, as you can see, right? I'm going to scoot that down here. Okay, and obviously I can equate things in the I and the j direction. So if I equate things in the I direction, then here is what I end up getting. So a naught on this side is going to be 4 by root 2 times alpha OA minus 2.12 square. If I equate things in the j direction, I get 0 because I have nothing there, is equal to 4 by root 2 times alpha OA plus 2.12 square, which essentially tells me I can solve for alpha OA. Okay, so I can find out alpha OA. Okay, and this is essentially minus 2.12 square. Okay, so I can then see that alpha OA is obtained for me as minus 4.49 radians per second square. And once I obtain this, I can then go back and then plug it into the acceleration of point O. Okay, so which tells me then that acceleration of O, which is 4 by root 2 alpha OA minus 2.12 square, is going to be the following value. Okay, if I do the substitutions, this is going to be 4 by root 2 times minus 2 times 2.12 square, or acceleration of O is going to be minus 25.4 meters per second square. Okay, so nice thing is I can now write alpha OA, which was assumed to be alpha OAK, is now going to be minus 4.49k radians per second square. You see, I did not know the direction to begin with. Now I'm told that this is actually clockwise and not counterclockwise. And then likewise, acceleration of O is something and something. So acceleration of O is minus 25.4 I and then 0j, so many meters per second square. And I'm almost done. All I have to do is go to the disk, apply the same equation, and then call it a day. Okay, and I appreciate your patience. So I'm going to zoom up a little here and let me look at the disk. Okay, so I'm looking at the disk. I'm going to grab some of these things. Okay, and I'm going to come here. Okay, so now I did come to the right place, but that wasn't that great. Okay, so now I'm going to call this as 2. Look at the disk. I can now say that acceleration of O is acceleration of C, alpha of the disk, cross R O slash C, omega square of the disk scalar multiplied by R O slash C, plus A O slash C relative, which is 0, 2 times omega of the disk crossed with velocity O slash C, I'm sorry, relative. And I can cancel off some of these terms. This is gone and that is also gone. Okay, and what are the things I know? Acceleration of O is minus 25.4 I and 0j, so many meters per second square. Acceleration of C, if you recall, was minus 4i and then something in the y direction, so many meters per second square. That's an unknown quantity in the y direction, I don't know. Omega of the disk, I had obtained it to be 3 radians per second. Alpha of the disk, I had assumed it to be minus alpha in the k, and then R O slash C is nothing but 1j, so many meters. Okay, then take all of these and substitute it. So this is 25.4i 0j. This is equal to minus 4i acy in the j minus omega square of the disk, okay, which is going to be 3 square times 1j. That's about it, right? Then I equate the I and the j terms. I terms on both sides. What do I get? There is alpha. I forgot the term alpha. Very sorry. This is going to be alpha minus alpha OA in the k cross j direction. So this is going to be k cross j is in the I direction. Okay, so that's what I'm going to be getting here. Okay, and so with all that said and done, I'm going to equate the I terms on both sides. So this is 25.4 and minus 4, and I'm going to have minus alpha OA. Okay, so this is what I have, and I think this is a negative. I'm sorry, I forgot to do that. Okay, so that's a negative, and then I do the j terms on both the sides. I'm going to have 0 is acy, and then minus 3 square. Okay, because that's the j term on both sides, which tells me that I can actually solve for the acceleration of point C completely. Okay, so acy is 3 square, which is 9 meters per second square, and which also tells me that alpha of the disk, I can obtain it. That's going to be minus 25 plus 4, or it's going to end up being a positive value for me. Okay, so if I do the calculations, this is going to be the following. K cross I is j, so this is a positive number. I'm sorry, once again, here there is a typo. I'm probably getting hungry for my breakfast, so all right, so this is going to be minus 21.4 radians per second square. So alpha of the disk, which I had assumed to be alpha disk in the K, will now give me minus, and minus becomes a plus, so I'm going to have 21.4 K radians per second square. And I can also write the acceleration of C is acceleration of C in the tangential direction, acceleration of C in the normal direction, which was the same as acceleration of B in the tangential direction, acceleration of C in the normal direction because of rolling without slip. And so acceleration of C is minus 4i plus 9j meters per second square. All right, let me end with a straight line. All right, so that's the end of this problem, and it's a nice problem in a sense that we walk through a lot of the aspects of rigid body kinematics here. Once again, the ideas are straightforward. It is just the application of the equation of velocity and acceleration analysis. The basic idea that I have used here is find a point that is common to the two bodies. In the beginning, it was point C and point B, and we were able to relate the velocities of those 2 points by using the idea of rolling without slip. And then I say, okay, point O is on point body OA, point O is on the disk. I find the velocity of O using information from the body OA. I find velocity of O using the information from the disk. I equate the two terms. And I do the same thing for the accelerations as well. And after going through all of this process, we end up having the answers as we have described right down here. Okay. All right. Thank you for your patience. I hope all of you are staying safe, staying healthy. Take care of yourselves. Bye-bye.